So welcome back. We're going to kind of pass between topics here. I wanted us to finish just the very high level introduction to OpenGL topic. I think you've gotten that introduction just by having to understand the code that's already provided for you and to make some entertaining modifications to it for purposes of demo. But I'll just walk through an example because I think it's kind of easy to kind of skip over a lot of the boilerplate that's happening, and I'll just try to explain as best I can what that's attempting to do, why it looks a little bit more like there's more overhead than there really is for the examples that we have been sharing so far this semester. And I also thought as a starting point that just reiterating this actually came up a lot yesterday in lab as people were trying to understand the lab document and try to understand what I was getting at with vertices versus attributes. And this is the best definition that I can come up with. So it's true in all graphics libraries. It's not OpenGL specific, but we have these objects in a scene and they're composed of primitives, right? So geometry. And those geometric primitives are themselves described or represented by vertices. So a vertex in at least modern OpenGL is a collection of data associated with a point in space, a location in space. So when I say something is a vertex, that's what I mean. It's the location of where this descriptor should be found, and a set of uh, data values that are associated with it. So I also use the word attribute, but it's kind of an overloaded term here. But those data values, which are the attributes, can include all sorts of things. It can include the colors, it can include coordinates for mapping textures, reflection information for lighting, and really now anything you want it to include within reason can be considered an attribute. But what we generally have with the vertex would be that location information. So you have the location, and we were staying mostly in the XY space right now, but I think we can think of the XYZ space, and we'll talk about W relatively soon here. Um, so you have this location in a four-dimensional space, and then you have all this other attribute data associated with it. So that's what we're specifying when we specify a vertex. It is at the very least the location information, and then it's more likely to be location information and things that are associated with that location. So today, when we talk about, we're going to talk about rendering lines today, rasterizing lines today. I already received a message saying, "Well, why are we even looking at lines? You told us we're not doing lines for the lab, but we actually are. What we're not doing is rendering line primitives. We could, but we're just not for interest of time. But the same approach is applied because what we're going to be doing is interpolating values, these attribute values between any two given points. And while we think of this triangle as this potentially three-dimensional object, it also has all this other potentially one, two, or three-dimensional attribute data as well. So when we look at the red color channel individually, you can think of the change in red as being a line, having a slope between 2 points. So the same algorithms we're using to render line primitives are exactly what we still use when we're rasterizing triangles. Even though the triangle is not a line, we apply the same exact approaches for that. So anyway, vertices are the actual position data with some other data potentially associated with it. And in OpenGL, we have vertices that are organized in this kind of server side or device side objects called vertex buffer objects or VBOs. And that's what you actually store in memory, all that information you need for all the primitives you want to draw at any one time. There's all sorts of different ways and different ways of laying out data in a vertex buffer object. You can store array of structures, you can store structures of arrays, you can have interleaving things, you can have to some extent you can have pointers to more custom data structures in your vertex buffer objects. So that's just our storage. That's where we're storing the actual vertex data. And then there is also on top of this VBO structure, you have the VBOs themselves are organized in these so-called vertex array objects. So it looks like overhead when we have this in our code, where we have a single vertex array object that seems to be doing nothing, and then we have potentially one or multiple vertex buffer objects. But what the VAOs allow us to do is have a logical organization of the different buffers we may want to have at different points in a given scene. And we can easily, by enabling and disabling different VAOs, enable and disable all the vertex buffer objects that can be associated with it. The reason that seems like overhead, and when we look at the red triangle code and you have that in MP2, um, it seems just like a lot of unnecessary logic. It's because when you're just drawing one thing, whether it be one scene of points like an MP1 or just one triangle, or even just a series of triangles only just drawn once. It does seem like overhead. We're not switching between any of that, but it gives you the ability to do that because in a real more complicated scene, you're going to have all sorts of different primitives you want to draw at varying times. And the VAO is one way to organize that data so that you can keep track of that without having to continually copy data and keep track of it essentially yourself. People are starting to see this for MP2, but just to reiterate, here are the primitives that modern OpenGL effectively allows you to support, at least without doing further geometry manipulation. But then, in general, to draw 3D things, you have to decompose them into one of these things. So, in general, if you look at the rendering pipeline, you can draw points, lines, and triangles, and you can use collections of those to kind of optimize your render. So, MP1 was just GL points. So that pointillism art demo was really on point. It was exactly a good illustration of what you can do with that type of primitive type. There's value in having points, but it's also really limiting as well, right? We were basically doing some sort of rasterization ourselves in software by sending lots and lots of points. So it's pretty inefficient as well. Lines also have value, but there's limits to what you would want and can do with lines. And then you have triangles and the related triangle types. You will also see code examples, certainly if you just look online using GL polygon, GL quads. Those are technically deprecated. They may still work depending on your OpenGL implementation, as we talked about the deprecation model. Driver providers can still choose to still support those older versions. But generally, if you see a quad example that you really like or a polygon example, you can generally replace those with triangle fans instead with a little bit of extra effort. So these are the main primitives you tend to see now. So this is our first real OpenGL program, if we're not counting the point examples as being real. This is the simple VRED triangle. And so this code is available in your MP2 project directories, and I'll bring it up here to kind of walk through some of the things that code is doing. It's just an example that demonstrates what it means to initialize that vertex data, to organize the data to be able to do rendering, and to build up, in this case, a single triangle from that vertex data. Your goal in MP2 is to get this to work in hardware, right? And we will talk, including today, about what that means and how we do the rasterization in hardware and how that all ties together. I wanna warn you now because I think you may forget about this otherwise. If you get this exact example working in hardware, my experience indicates your rasterizer is maybe about 60% done. So you get there. This is a very nice, well-behaved, boring triangle that doesn't stress many of the aspects of your implementation. It only has red, so if you're screwing something up with other attributes, you won't be able to tell. It has a nice aligned, bottom edge there. So if your algorithm has got some weird issues with how it's traversing the triangle, it may not get detected there. It has a nice regular shape so that the traversal algorithm itself is going to have a very consistent kind of flow as it zigzags through the triangle. Get this one working. You're a good part of the way done. But then at the very least, start to manipulate the vertices of this triangle and confirm that that is working. And there's other applications that stress test it a little bit more. But certainly when you're wanting to simulate triangles, when you're wanting to check on the ILA what the data is looking like that's coming out, um, starting with just a single triangle is still oftentimes the way to go. So our version of OpenGL supports the primitives that are listed on that slide. But our raster, I mean, it's up to us what we support. We certainly support GL points. And if you do MP2 correctly, you'll support all the triangle variants. But that's basically our limit. So modern OpenGL is less focused on supporting different types of primitive types in the specification itself, but it provides more hooks for you to be able to manipulate geometry. We're limiting ourselves to kind of the vertex by vertex manipulation, which does limit the kind of interesting kind of deformation effects and other things that you can do, but it's pretty sufficient for specifying all sorts of really cool 3D scenes here. So we have the VAOs, and let's open up the code here. I should have it open here. So the first thing we'll see, beyond all the, hopefully everyone can see this well enough behind me, beyond all the other GLFW and stuff that's kind of become our boilerplate here, you do have that initial kind of initialization of the vertex array object, and that's just those 3 lines of code here. It seems unnecessary for the code. I mean, it's required, but it looks unnecessary for the code that we have been running all semester. because we only have one of them, and we're never changing the one that we have, at least in the examples we've used so far. Nothing from our hardware perspective should preclude us from being able to handle that, to be able to handle multiple VAOs and switch between them relatively quickly. It's more of a driver side thing, like a SGP graphics.c driver side thing, where are we handling the data structures correctly? Are we keeping track of what buffer objects are associated with which vertex array objects? I haven't tested it, but it should generally work. And if you want to have a scene that has more complex swapping between primitive sets, you should be able to support that. From a hardware perspective, it's agnostic to what's happening with regards to that. So that's the VAO that we start with. So you have a name associated with it, and that's or uh, a counter or a data type associated with it. That's your gen vertex arrays, and then you're binding the vertex array. And then in theory, you would then update the buffer objects associated with the VAO. Um, and it's just a way of encapsulating all the different VBO data associated with an object. So it's generating name, although it's not a name in the sense that you think of a name, but it's a OpenGL attribute associated with it. You make it current by calling bind vertex array. If you never have any other VAOs, you never need to call that again in your application. Um, and the code winds up looking very similar to what we're already doing for the buffer object that you've been playing around with so far. So when we're storing those attributes, we have the data stored in a VBO and then associated with the VAOs. Um, there are many different ways of doing it, but specifically, you're going to generate the quote unquote names again with a similar call called gen buffers, and that's what's happening here. So we like all those memory objects that you have in OpenGL. It's created using the very similar set or subset of functions. So you generate the name calling gen buffers. You would want to ideally make the certain specific buffer current by calling bind buffer. I think when you call gen buffers, it makes the first buffer current, but otherwise you want to be explicit and say, this is the buffer I'm actually going to be um, operating on for the future calls that we have here. That's a bit of state information that the driver keeps track of. And then we actually have to copy data into that buffer. So let's look at what that looks like from the OpenGL coding perspective in practice. So actually ignoring the actual data that we have stored here, we like global data, so we can manipulate it without thinking too hard about it. So here's a very similar set of function calls then associated with generating the buffer object, providing a name for it, binding it to be the current buffer. This is the one that any future calls are associated with. That'll be the buffer using that same generated integer ID, and then actually copying data into it. That's that GL buffer data. So that is associating a region of data in your application's memory with the buffer. It is not necessarily, and certainly if you look at the OpenGL spec, it's not necessarily copying data. It looks like it should be. If you look at the function call, GL buffer data sounds like it buffers data, but it doesn't necessarily do so, and OpenGL spec doesn't say that it does so. In fact, if you look at our driver in the graphics.c, we actually wait till a little bit later, because this just specifies there's a blob of data, this many bytes, which is all this is doing here, associated with this pointer. And there's different modes of how we want to buffer our data or associate our data, but this is a very common one. Also, there's lots of hedged language in the OpenGL spec about what the different modes for buffer data are guaranteed or are just hints to the runtime to do. But in any case, we declare the buffer. Here's how many bytes are associated with that particular buffer. And it's actually only later when we declare that part of the buffer data is corresponding to an actual attribute for a set of vertices. Do at the very least, we know that we want to interpret those as floating point data. So in our sgp _graphics.c, I want to do all the type conversion in the driver versus having some hardware that's doing type conversion, which we could also have supported. So we actually wait, if you look at the code, until we get this function to copy the data into the device. It's only at that point do I know for certain what type it is and whether it's normalized or not. And so I wait until then to copy it into the device. The spec doesn't say when actual data copies should happen. That's your bind buffer and buffer data calls here. And then there's different ways you can actually copy the data or specify, the range of data that will eventually be copied. So we got to be a little careful with it, right? So this is generating the buffer, this is binding the VBO, the buffer, and then this is initializing it with data pointers, saying this should be the data associated with that particular VBO. This is telling OpenGL, somewhere in OpenGL we have to allocate, for whatever that means for the OpenGL runtime, that amount of data. And this example on the slide, which is different than our red triangle example, is actually, instead of generating two VBOs, right? If we go back to our example that I have open in code here, we have two separate VBOs, one for the vertex position data, right? So even that's a little misleadingly named. One for the vertex position data and one for the color data. And we're calling our buffer data calls separately for those. That's actually not a requirement, right? The function here takes amount of bytes to associate with a buffer object and a pointer associated with it. And then there's multiple different ways you can do it. So in this case, the example on the slide is showing for a given large array, as opposed to having separate position data and color data in two separate OpenGL buffers, just have a single one. And then there's a call for buffer subdata, which is saying we're actually starting at this offset 0 for what we're going to associate with the positional data, and this offset, which is basically the halfway point with what we're going to associate with the position data. There's a lot of different versions of OpenGL in terms of how they treat floating point data. GL float is meant to be single precision floating point data of the IEEE 754 type. We then interpret it as fixed point data because OpenGL spec says here's the data types you're supposed to be using, and then there's a whole different subset of the specification that talks about required precision of actual computation. And that's actually also a bit of a moving target. And the trend is not in the direction you may think, as opposed to trending towards allowing more and more precision as an expected use case for this type of data. It's actually less and less precision is what we're seeing. So you will see all sorts of IEEE and non-IEEE compliant floating point specs being allowed in an actual OpenGL implementation. Again, for the same reason that we're okay with fixed point, right? When you're ultimately rendering data to be viewed on a screen versus something that's meant for computation, well, there's only so many colors our screen can support. So there's only so much precision that's needed. There's only so many locations we can ultimately put a fragment in memory. So there's only so much precision needed for that as well. So that's those kind of trade-offs we actually see in sort of the opposite direction of, with computation, certain applications need a lot of precision, others can survive with significantly less. For rendering specifically, we specify these GL floats, and then the spec separately says how much precision you want the data, or you can require the data to be treated when it's actually to be the rendering application is to be started. And finally, although we're not really talking about shaders quite yet, we actually have to then finally associate or connect the vertex shaders with that vertex data. So we have to specify which vertex attributes are going to be issued to the pipeline and what locations those are going to correspond to. And that code is something that I think probably if you're looking at it just for MP1 and that's the first time you're looking at it, it may have just been, well, let's just kind of ignore this. And a couple people who were struggling with OpenGL, like making their own new applications for MP1, this may have been the part where it was kind of falling apart. We do actually have to specify where in my vertex shader my input data is going to correspond to. I have buffer objects, I'm buffering data. Where in my buffered data do I connect it to the actual vertex shader? And I think it's very easy to kind of miss that connection because for MP1 and continued for MP2, we're using kind of default shaders. And you can look at the code for that, and it's not doing anything all that interesting. It's passing, take input vertex, set it as output vertex. Effectively, it's what it's doing. But as part of that, it is explicitly setting different IDs, different locations in the shader itself for where in these buffers that the shader is going to be accessing, where is the offset associated for each individual invocation of the shader, which offset is going to correspond to, for example, position data versus going to correspond to color data. And that is what's happening in these calls here. We're explicitly saying, okay, I'm going to be enabling attribute 0, and this is corresponding to the vertex shader itself. Attribute 0 I'm enabling, and it's going to correspond to that pointer. Doesn't look like much, obviously, right? This looks like, well, there's the different parameters here. For attribute 0, we're going to have 3 floats that aren't normalized as input to that attribute 0. And actually, this is a pointer offset of 0, but it's going to correspond to what the currently bound buffer is. So we're going to bind now and say the active buffer we're referring to is the one where we specified position data up above. And here is how it's going to get pointed to by our vertex shader. So the way we do it in our lab infrastructure, not cheating, but it's making all sorts of assumptions along the way. We are assuming we have 4 possible attributes per vertex, and they're each going to be 4 wide vectors. Now, part of that's okay. OpenGL also says that even if you're only using 3 out of the 4 values and specifying it, it's going to pad it and make it of size 4, and there's rules for how it does that padding. So that part's okay. But there's a much larger number of attributes that it can allow, and different combinations of it. Whereas we're saying, well, how we're doing vertex fetch, we're going to have 4 attributes, basically 16 fixed point values we're going to associate with each vertex in our system. And this is how then we're connecting the two. For location 0, that's fixed point value 0, 1, 2, 3. That's going to be our positional data. For our code to work correctly in hardware, you'll have to be passing positional data for that 0th attribute. Likewise, in our render output, vertex shader, maybe we don't have to be that aware of it as of yet. And so as we write vertex shaders, you can kind of move things around. But if we're just passing things through as we're doing now, we are also requiring, based on what render output is doing right now, that the next attribute, the next 4 fixed point values, is going to correspond to the color data that we have here. And that's what's happening with this vertex attribute pointer. So we're saying we have an attribute 0, we have an attribute 1. In this case, let's associate a different buffer with each one of those, and then vertex fetch is going to connect all those together and assemble the vertices to be passed down the rest of the way on the pipeline. And the rest of this is just a different option. So in this case, we're specifying X, Y, Z, and RGB. If instead I just wanted to do X, Y, and not X, Y, Z, which if this is all flat geometry we're doing, you may want to save on some bytes by doing that. You could just, you would want to actually change the layout of the array of vertex data, but you could just change that 3 to 2. Likewise, if you only want red and red shaded things, this could also just be 1, right? And you could just specify the red. Or if you really cared about alpha information, then maybe you'd want to change that to be 4. But we're going to be padding that to be 4 no matter what you're specifying for that. And that part, at least, is part of the OpenGL spec. So that's that connection between buffer object data and then the attributes as the vertex shader sees them. And actually, the example I have here is actually a little bit different. But there's the flexibility of OpenGL is also kind of the downside there, that there's different ways to plumb it together to have the mechanics for how to connect it. The way this, if you look at the OpenGL example code I provide with the MP assignments, the way they do it, they tend to do it in their programs, is by doing explicitly a lookup in the shader. And if you see this call, it's exactly doing that, as opposed to assuming what is what, as opposed to assuming that position is 0 and color is 1. For arbitrary shaders, it's saying, for the shader this code is running, I'm expecting to see it would be a type of an input primitive type in my shader code called vPosition. There's no requirement you call anything vPosition. That stands for vertex position. You could have called it foo bar. It doesn't matter. But in this case, it's saying for the shader that this code is running with, there's going to be, think of it as a variable in that code referred to as vPosition. And the location in which I'm going to be copying that data then isn't going to be arbitrary. It's going to be associated with what that turned out to be, which it depends on which version of OpenGL you're talking about. Sometimes in older versions, you have to be very explicit and say there's location 0, 1, 2, 3. Other versions just say create all your input types, your attributes, and the compiler will figure out what locations they wind up being. And from your application's perspective, you don't really notice and you don't really care because it's whatever it returns, that's what we're going to use when we want to copy data to that particular that input variable for the vertex shader as we're assembling our vertices. We care in hardware. That's why this approach doesn't work out that well for us. If we were to use and support this particular approach for arbitrary vertex shaders, our vertex fetch unit would have to become a much more complicated piece of hardware. That's a potential project idea, right? If you want to be able to support slightly more realistic vertex assembly modes, there's lots of ways you can do it while still keeping the rest of our kind of pipeline flowing infrastructure in place. But that was an early trade-off made. It's still probably the right decision, but we'll see the downsides throughout the semester. And the only other difference in this example from the red triangle example is because that example has just a um, a single vertex buffer. You can then associate the attribute with that same buffer object, but the offset is what matters. And that buffer offset's just a little macro. It's that same void 0 pointer, but for the position data, the offset 0, and for the color data, it's actually the offset of after all the positions are done in the array, then the color data starts to be specified. So arguably, I mean, there's nothing wrong with this code, but this is our main render loop here. A couple of these things really don't need to be in this render loop. So we do usually want the clear call in the render loop. Before we start drawing to the buffer, presumably we'll want to clear the buffer. We haven't talked about use program yet. We won't talk about it that much yet, but that's kind of a one-time thing. I want to change my shading programs that I'm running. Well, we only want to change it once, so you could move that outside. I don't think that hurts us from a performance perspective, but it doesn't need to be there. Likewise, um, this mapping and connecting of attributes and their pointer locations in our shaders to buffers that we're specifying in our OpenGL code and eventually copying that data over into the GPU's memory, that also potentially only needs to be done once. If you are not changing um, the data that you're wanting to copy over, and in this case it's all static data here, you really also need to do that code once. And then finally, the final part of our draw, and so this is enabling and then disabling. You really don't need to do that either, right? You're enabling it, and if you're not changing the shaders that you have here, enabling it once and never disabling it would also be perfectly appropriate. And then the final part of the call is just that draw call. So we're specifying for, in this case, for continuous groups of vertices, we're specifying the primitive type we want the vertex data to be treated as. I believe this is the offset of from one vertex to other, how much we want to jump in our buffer object memory space, and then the total number of vertices we want associated with that draw call. So this code, which just runs the triangle shader, and I should just confirm that it actually works, but it should. It looks like that. If you were to run that in your MP1 hardware or your not yet complete MP0 hardware, well, what would you get back out? You'd get back out that exact set of vertices with color information associated with them, but they would be interpreted effectively as points, right? Because there's nothing in your hardware that knows any better, that knows right now at least until you make those changes, that knows whether or not I should probably make it first, that knows whether or not a vertex is anything other than a point. That was our MP1. Well, that doesn't seem right to me. Maybe I need to save it here. I might be in the wrong directory here. What would have happened? That definitely should not be drawing it as a. Okay. I was a little worried there. What would have happened? I think I didn't save the file. And you may look at this and say, well, it doesn't look like much. Well, this is without that big point shader that I had by default for the MP1 examples, because a single point in a 1080 by 1080 screen is going to be really hard to see, right? Even a red point on a light blue background. So it looks like we're not really drawing anything at all. But that's if you ran this code on your MP1 infrastructure, that's what you would expect to see. Effectively nothing, right? Because we're just then treating that same exact set of vertex data um, as just being associated with point primitives versus being associated with triangle primitives. So the primitive type is pretty critical. There's no denying that, right? So OpenGL has all sorts of rules about the type of polygons it is guaranteed, or the compliant implementation should be guaranteed to display or render correctly. We could talk a lot about different rules about whether it's simple or not. There's the definition for simple is you don't have any crossing edges. So one can, in theory, define a quad that has vertices in this order, and you're going to get something different back out when you specify that OpenGL. Likewise, non-convex. Convex is that if you take any 2 points on it, you should never leave the shape when you do it. And then flat, all being in the same plane. It's much harder to visualize a non-flat polygon in a 2D slide here, but um, you're really depending on your user program to check that you're having your shapes being that. The nice thing, though, at least from our perspective, is that triangles are guaranteed to be all three of those. It's guaranteed to be simple. There's no way to have anything crossing because it's just three lines here. It's guaranteed to be convex, and it's also guaranteed to be flat because if you have 3 vertices, by definition, that forms a plane. So they're guaranteed to all be in the same plane. We can specify invalid triangles in our OpenGL application. Um, we can try it. I mean, see what happens. I haven't actually experimented with this. Um, if instead of having that data, so -9, -9, 0, 9, if I change that third point to also be -9, -9, that would no longer be, really wouldn't be a polygon at all, right? It would have 2 points that would be collinear or on top of each other. So it would not be a triangle back out. In general, when you specify something that's invalid from the geometric perspective, OpenGL will not throw an error. It has no real way of knowing this as it's just sending out vertices. What your rasterizer is going to do is going to depend on your hardware. And so, well, let's see. Maybe it'll look great. It drew nothing at all, which is probably a good outcome of this implementation of you gave me something invalid and it just didn't give you anything that got rendered at all on the output side. Your rasterizer that you're building for MP2, I don't know what it'll do. If you provide something that has an area equals 0 triangle, um, I'm not sure what would happen. Oh yeah, and Brian, your point's absolutely well taken, right? If you need a star shape in your design, you can obviously do a star shape. You just can't do it as a single primitive in terms of how we fill it, right? So you would do for that one, I think you'd have to do it with just multiple triangle. Oh no, you can do almost anything with a triangle strip. So I'm sure you can do triangle strips for this one at least. Maybe this one you just do with 2 separate triangles if that's the shape you actually want to draw. So it's not limiting sort of the modeling side of things of what you need in your system. It's just limiting for an individual primitive what that primitive can look like. Yes, what I just did would be undefined behavior in OpenGL. At least to my knowledge, if you're not specifying polygons that fall under certain limitations, you'll get what you get, and you can't complain when you specify something like that. It's nice that it doesn't crash. Pretty sure, unless you make some special checks for it in your hardware is going to lock up when that happens. But let me know. Let me know what you see when that happens. In fact, there's one of the applications we run as our benchmarks for MP2 is called rand triangles, where it just generates a bunch of random triangles. And I have confirmed that for the random number generator on the Xilinx machines, it's just fine. We're going to skip this demo for now, um, or this example for now. Um, I have confirmed that for the number of random triangles that get generated by default, none of them are invalid. I cannot guarantee that as you play with that number or change the random seed or do other things that you'll have valid triangles for every one of those. Um, it's hard. I mean, if you take a random number generator in a floating point space, you shouldn't get 2 random numbers that are the same in a row. But there's no guarantee that that's the case. So that's a very unsafe piece of code that it can lock up your board if you play around with it enough. But we've gotten enough experience with locking up our boards even in the last week, so we're not afraid of that when it happens. And sometimes it kind of improves things by doing so. I didn't open up the shaders associated with this red triangle example. It's very similar to the shaders we've already been using. Just very kind of not exactly default shaders. I would call them pass-through shaders. There's other shaders that are would be better referred to as default shaders that are doing some very basic vertex processing on them. This is more just passing data through and doing nothing with the input data. So we've kind of kept our version of OpenGL a moving target, so don't worry so much about that. But here, when we were talking about attribute location 0, attribute location 1, that's what that's corresponding to. So this is a vertex shader on the left here, and it's saying my vertices are comprised of 2 attributes, and they're both of size 4, vec4s. We'll talk more about this when we actually dive into shader architecture and the resulting assembly, what this would look like for it. But that's what that's specifying in the shader. I need to specify um, data for two attributes for every vertex that's coming into the system because I'm running this shader. But then it's not really doing anything. There's all sorts of required output data from a vertex shader that depends on what version of OpenGL you're on as well, and then which ones are allowed to be defaults and which ones are not allowed to be defaults. One reasonable rule that you should take into account is you always have to specify the position of the outgoing vertex. So in our case, we're specifying an input vertex position. That's that -9, their -0.9 data that was in the red triangle example. And the shader's not really doing anything. It's just copying it to the output. So take that input attribute that's per vertex and just copy it to the output. Likewise, we're specifying color. There's no requirement that our vertex shader does anything with color at all. And if I commented that line out, we would just get a white triangle back out because that would be the default color in our fragment shader. But in this case, we're saying we do want to specify per vertex color information, and consequently, vertex shader is not doing much. It's passing it through. Okay, you've specified this. We're not implementing anything in vertex shader hardware quite as of yet, so we're just going to pass that data through. Um, Likewise, the fragment shader has slightly different requirements about what can or what must be implemented. In this case, it's also really what we're doing by default, what we're calling pass-through.frag here. We're also specifying a pass-through fragment shader. Uh, we have an input position, and we're not really doing anything with it. We would have to be careful. We do want to make sure we're actually passing that information back out to just declare where it needs to go on the screen. We need to actually have that position data still. But in this case, we're saying our output color is just what our input color is. So it's not doing anything all that terribly interesting yet. It's still the requirement that you have that there. And then a lot of our OpenGL code, the plumbing of that or the mechanics of it is associating data specifically with our input vertex and the attributes. The more explicit you can be about position information, I think the easier it is to look at a piece of code and connect it to what's happening in your shader to what you're seeing on the screen. But then you'll see they do have to kind of go hand in hand, right? So you write a piece of OpenGL code, and unless you're using some very arbitrary kind of shading library and OpenGL shading loading library that's a little bit more general purpose than the one that we are using this semester, um, your OpenGL code has to reflect what's in your shader. So if you change your shader in a significant way, not the logic inside main, but maybe the input attributes it's expecting, your OpenGL code also has to change. There are a lot of these required, and they're all prefixed with GL underscore required outputs of the vertex shader. I'm positive you have to specify GL position for a valid vertex shader. There's a lot of other ones that are all kind of connected together, but we get by in this semester by assuming defaults for most of those and specifying for our four vertex attributes up to four input vertex attributes, each of type vec4, and up to four output vertex attributes, also of that vec4 type. That's enough, I think. You could do some pretty good shading with four input and four output attributes. It's not terribly limiting, especially because they're of these vec4 types. So you may want to do things that are just scalar types, and then you can combine them together and call that an arbitrary vertex data attribute that you're using for multiple purposes. So it gives you enough, I think, of input variables to play with in your shaders that you can start to have some fun with it, I think. I do want to briefly talk about the back end of what's happening in the shader compiling because you're going to start to see that very soon here. But it's becoming something of the default spec, if not really already, of using this SPIR-V or SPIR-V representation as kind of the binary intermediate language for defining shaders. It's required if you're using the Vulkan API, but it's an option in OpenGL, and it's becoming more and more kind of the expected option if you're writing modern 2021 OpenGL code. I would argue yes that it's likely to become kind of the default way of distributing shaders. I see some benefits and I see a lot of downsides of doing it, but I think it's the future. So being aware of it is necessary. So at least at the very least, it separates the shader source from what the vendor, and I'm talking NVIDIA, AMD, and others may be doing in terms of their implementation of vertex shading. At least in theory, I don't think in practice, but at least in theory, it allows for cross-compilation capabilities in which someone could be using GLSL in one project, someone else could be using HLSL in another project, and they all kind of work together. At least they can work together because they're targeting this shared binary intermediate representation. If you think of LLVM and what that provides as a shared intermediate representation, there's a lot of commonality with what SPIR-V is attempting to do here. It's probably faster for loading. I think that's a bit of a hand wavy argument that you're loading a binary blob versus a text blob, and maybe for applications that are significantly shader heavy of the type that I don't have much experience with, there could be some real performance savings there. And likewise, I think that's a bit of a hand wavy argument, but that's one of the arguments made for it is that because it's a binary distribution format, you're not distributing source code for your shaders with the rest of your application. You're distributing this binary blob. But that's really just obfuscation, right? Because there are tools to kind of go back to shading language from the binary blob, and we make use of those tools this semester. Just to give you an example of what it could look like in your Spear V code, this is a slightly different vertex shader here, where we're actually not specifying any input attributes at all. We're just specifying an output attribute. So we're saying here we have an out vec called outColor, and we're actually hard coding it. So give me a mostly blue with some red and green highlights output color vector here. That's the GLSL shader example. When we run at least the reference compiler, it's called GLSlang for an LLVM style interface for compiling this language, we get this back out for the um, well, I mean, technically we get this back out, right? We get the binary blob out for our Spear V, and then you can run a disassembler tool to see what that pseudo assembly kind of virtual assembly, a virtual ISA format winds up looking like for your Spear V example code. Um, Everything looks MIPS like if you know MIPS well enough, right? If you really remember what you did in that 381 or other architecture class. Um, there's some things that take a little getting used to with this. I'll say Steve and I, he's here today, are still getting used to what's happening here. But it all at least has some logical sense. So you have labels associated with either datas or operations, and then you compose them together to specify. In this case, we're not doing very much. There's no actual math here, but we're specifying that we have an output uh, type that is going to be a vector 4, and we're going to compose that by having point 0.4, point 0.4, point 0.8, and 1.0, and that's exactly what happening here in this instant composite ISA or assembly instruction here. We're saying compose for that output type a composite that's point 0.4, point 0.4, point 0.8, and 1.0, and set that as my output type. You can definitely play around with that reference compiler. Starting in MP3, we'll be providing as part of the driver infrastructure that reference compiler um, to see what kind of assembly gets generated, and that will be your challenge. So we actually then translate this to a little bit more of a 381 style SIMD ISA as opposed to trying to implement this directly. But it encodes all of the same exact information, but the ISA becomes a little bit more human readable for our purposes and something you're more familiar and comfortable with. And that's what we'll be implementing when we get to MP3. It will be uh, doing vertex shading for a somewhat constrained set of assumptions for what we can allow in our vertex shaders and connecting that to the rest of the pipeline that we have in place. And that's when you're going to start to see that, okay, I can do what I want with my OpenGL code. I'm not really constrained as much anymore with what I want to specify either on the input side or what type of processing I want to apply to it. Right now, we're not doing much, right? We are specifying our geometry to fit into this -1 to 1 range because we're not doing any vertex shading whatsoever. And if we do something outside that range, it's just not going to work. Well, we can start to break that and all sorts of other assumptions once we get to, say, the end of MP3. I've been talking a lot. How are we doing? Are we okay? Um, I mentioned this before, the Shader Toy website. Did anyone get a chance to check it out when I mentioned it last Thursday? Don't say no. You're supposed to go to that. So, okay, a couple of folks did. I knew you would, Micah. I would suggest we go there for a demo. The downside is every so often it locks up my laptop. So if this Zoom meeting appears to have ended when I click on this link, it hasn't actually ended. Come back and I'll restart it, and that's just my computer breaking down. It is a totally different set of rendering algorithms. So um, I think Graphics Genius is a reasonable description for Inigo here. He uses this concept of ray marching for sign distance fields, where he mathematically describes all the different geometry in the scene and can do effectively a ray traced type implementation by just evaluating those mathematical functions. And for certain mathematical functions, you can get very efficient implementations of detecting the light in a scene and the color in a scene based on just that type of 3D geometric mathematical description, it's pretty significantly different from the kind of shaders we think of as being in traditional OpenGL. And it's WebGL, not OpenGL. The actual approach he takes, if we were to connect this to what we are doing in this class, is the geometry in the scene that all of those examples used in Shader Toy is effectively this: a single quad or a single triangle fan that covers the entire screen. So the actual vertex shaders in this example, they really don't exist. They're trivial or non-existent vertex shaders for all of these Shader Toy examples. All that's happening here is on the fragment shading side, where each individual pixel that gets generated, or fragment that gets generated in what the rasterizer, um, and it's using that somewhat high level math to describe what's happening for each of those individual values here. So I will open this up. Maybe that was my attempt to open it up, and it just gave up on me. Everyone else can also open it up as well. If I see you drop from the Zoom call, I'll know why. Um, oof. Okay, so there is a lot going on here, and it's it's a little bit beyond me. I would say, not just beyond the scope of this course. We are slowing down very quickly. That's not my voice slowing down. I was slowing it down intentionally. Let's see here. It's struggling. But this, I would say, fairly realistic image is just coming from a relatively simple mathematical description of what's happening here. And you could play around with this and play around with the different descriptions here. Let's see. What's something I can change without really breaking things? Um, oh, what would happen if I change? Shall we have? It's not letting me click on anything. So anyway, play with that in your own. Yes, everything is struggling right now. I'm killing it. I'm failing to kill it. I'll be curious to see how that got recorded here. Play around with that offline, I guess. But what it is powerful math in the sense, but relatively straightforward math being applied to incoming fragments that are specifying that for every location in that just scene here, um, what should the color of that individual fragment be? And that's all that's happening. So it's really doing no vertex shading at all. This is not being specified. This I'll call it Pixar class type of rendering of a scene. Um, this is not being specified with geometry as we think of it, with regards to this being composed of triangles and having really clever lighting models applied to it. It's the other way around. It's the individual fragments and then mathematical shapes describing the scenes and their interrelation, which we then determine from that what should the actual location should be. Yeah, Matt, that should have been my GPU on this laptop doing it, but I think the GPU is also busy running a couple of other pieces of software right now. So I think, good. There's still need for innovation in graphics hardware, right? There's only so much we can do with existing things. So when you get a chance, I guess not right now. Um, Play around with that, change some of the mathematical functions for it, and you can kind of. I'm not artistic. I can make it look ugly very very quickly. That's about the main contribution I can do. So at least play around with it. Yes, that's. I gotta be a little careful with the phrasing of that, Brian. But yes, it's describing shapes, but it's not describing OpenGL style geometric shapes where everything is a triangle. It is describing a mathematical model of a scene and tracing effectively where light that's hitting the scene is interacting, where it's hitting which piece of geometry first. And so that Inigo's main, if you look at his dissertation, it's on Bezier curves and how to very efficiently model different types of shape using modifications of that and algorithms for doing that kind of rendering. And so Shader Toy is playing with that very particular style of shaders. It's not playing with what we think of as OpenGL shaders, where we have a vertex shader and a fragment shader and maybe geometry shader as well. It's um, hardcore fragment shaders that are applying a lot of math to determine that for every XY location on the screen, what should that particular color be versus what we do, which is we start with a triangle and then we compose those triangles to kind of make our scene from there. So we're not really shifting, but we do need to get to this topic because we've spent a lot of time kind of gearing up, but we're falling a little behind where we are in lab. So certainly we know where we are in lab right now is right here. So we're giving an object. We have this object defined by the vertices, and we're getting closer to understanding what that means. But so we have these attributes. So given this vertex data that has position information and other information associated with that position in a 3D space, what do I do with that information? How do I go from vertex to actual triangles? And that's what this term rasterization is referring to. So we have to be aware of, at least in the beginning, what is the actual shape of the object. And I think we're okay with regards to this, but for MP1, we were assuming that our geometry was just the vertex. That's only true in the case of GL points, where the actual vertex is dictating what we want to have for our geometry. For all of the other types, we're composing these vertices together to create these higher order primitives here. When it comes time, some of the vertex shading still is applied on a vertex by vertex basis, but when it comes time to actually fill it with color to determine what is happening inside this shape, we need to be aware of what's happening in the actual shape. So our pipeline hasn't really changed in terms of what's happening here, but now we really need to focus on not on the vertex transformations, which I'll wait till later. This kind of middle ground here. So what happens when a vertex gets sent through the pipeline, and what should the output be? There's a lot of other things happening on here as well. There's this whole separate pixel pipeline, even for the OpenGL 2.0 model of things. There's the whole display side of things. We've covered a little bit of that. We've implemented a little bit of that. We're going to focus on this middle part here of vertex comes in, potentially transformed. For MP2, it's not transformed, but it's specified as if it was already transformed. How do we get fragments back out? We'll do our best with it. So this is our old school fixed function OpenGL. I don't think I need to run the example to show you, but this is specifying that if we had a GL triangle strip, I think I mentioned that I like sharing the old school fixed function OpenGL examples because I think, for me at least, it's easier to see exactly what's happening for simple shapes at least. In this case, we're specifying a triangle strip, and for each of the vertices in the triangle strip, we're setting the state for the color, and we're setting the location information for it as well. There's a couple other tricks happening here. I'm setting a view of the system, which we haven't talked about at all, so that we can actually specify our vertices in screen space. It's completely valid. It wouldn't work on your board because we're not doing any vertex transformations yet. But in terms of laying out on a screen what you want your shape to look like, this is a pretty nice way to specify. This is a pretty nice way to specify what geometry we want to display on the screen. So we set color of halfway green as our starting place. This is in our XY coordinate. We're specifying vertex 1 is green, vertex 2 is also green. Then we shift to red, move things over here, specify red, red. We get our strip that gives us that kind of trapezoidal shape back there. So the challenge of the rasterizer is for those input vertices, we know what the corners are, or the points on the edges are, right? Because those are the ones we're explicitly specifying. We're saying this one is green, or halfway green, and this one is red. The challenge is what everything else is inside it. And that's what your rasterizer is doing. It's easiest to visualize rasterization when talking about color. And I saw that the way the pre-lab was written, it's not your fault, but I saw that was tripping people up for the MP2 pre-lab. Color is just one of the attributes. So at the very least, if we were just doing flat geometry on a screen like this, we would want to interpolate or rasterize the red, green, and blue channels of those individual fragments to get this kind of, reddish, greenish, I apologize for colorblind folks, this reddish, greenish kind of a color that we have going on here that kind of looks brownish, as you're combining all those colors together. That's the very least we have to do. When we talked about the shaders and the attributes and connecting it, we have to do that same exact rasterization task for all of our attributes. So if we're specifying X, Y, because ultimately this is going to be displayed on a screen here, everything else needs to be rasterized. So not just the color information, which is the easiest one to visualize. If this was a three-dimensional shape, we would also want to rasterize that dimensional information as well. The Z information we would want to rasterize as well. Because we're specifying this triangle, it's going to be displayed on a screen. We can only see the XY, right? In terms of where it is ultimately on our screen, it gets flattened, right? Eventually, we lose the depth information, right, when we actually ultimately draw it on a screen. We avoid that for now because we don't do anything with the depth information. But eventually, even if we do all that processing, we have to drop that depth information. So we have to determine that from an XY location, what are the individual attributes as we walk along that line, and that includes depth, that includes color, and that includes all the other attributes we specify that maybe aren't something we can visualize at all with what's happening here. We just know that it's some information that we've specified on a vertex by vertex basis. The definition of a rasterization based rendering system, either hardware or in software, is that we interpolate those values as we generate the individual fragments associated with it. So we give a range. This one is green. This one is red. As we move across, we get greenish red. The reason I didn't entirely follow in terms of overextending it, if we drew edges here, it'd be a little bit more obvious because it's a triangle strip. It's rendering two different triangles here, right? It's not just you're not rendering an actual trapezoid. And if you were specifying as an actual trapezoid, there may be a different way you'd want to blend the color from left to right happening here. But we're not. We're not rendering a trapezoid. We're rendering two triangles. Well, yeah, that'd be cool if it was. We generally don't have those, right? So we want everything to be triangles because the algorithms for rasterizing triangles and the associated lines as we're interpolating attributes are well understood, and it's something that we can build relatively efficient hardware to do correctly. Um, let's talk about vertex assembly first. Talking with teams yesterday, I think you had a handle on it, but I did want to make sure that everyone in the class kind of appreciated what we were doing with this. So there's the vertex assembly step that we are doing for you, but that's some sort of way of assembling the vertex. I call it vertex fetch, but vertex assembly would have been a perfectly valid name for it as well. We are specifying in our OpenGL code all these VBOs, all these buffer data. We're specifying in our shaders all these attributes. And so there needs to be a piece of hardware whose job is to assemble all that together. I made that module as simple as I could by making certain assumptions for the hardware that you're using, which is everything has 4 attributes. They're all vec4s. Grab the next 16 things from memory and combine them together and call that my assembled vertex. In practice, though, that can be a pretty complicated piece of hardware because there's a lot of flexibility in terms of what would the attributes be and where they would be stored in memory. We get rid of all those complex assumptions and say it's a big chunk of memory. Here's my attribute data. FIFO that into the rest of the system. But that is our vertex assembly stage. You can think of it from a data structure perspective that for that trapezoid example here, you would have a vertex that would specify what is my XY information with Z and W being set to default. It should be 0 for Z by default and 1 for W. We'll talk about W eventually. And then for some sort of internal representation, whether it be float, whether it be our fixed point format, specify what the color information would need to be as well. And that you could think of that as a data structure in your software, but it would need to be in practice a very flexible data structure because of the different ways one could have attributes associated with a given vertex. There would probably need to be other things here as well, including like relative position data, offset data if we're interleaving things and things like that. But at the basic case where you just have a set of vertices coming through, you're going to have position and potentially color information associated with them. That's our vertex fetch module. It's a lot easier or simpler than it would need to be in practice for a quote unquote real pipeline here. There's the set of transformations. Haven't talked about that at all yet. We will get there. That's now how I manipulate my geometry in a vertex shader is by applying certain affine linear transformations to it to move things around, to stretch them, to shrink them, to rotate them, to do all sorts of things with my individual vertex basis. We're going to be applying a lot of linear transformations to our input vertices, as well as potential other things as well. If I want to figure out what texture coordinates should be associated with things, I want to potentially calculate it there. There's basically now with programmable shaders, whatever math is within reason is something that we can do in that vertex transformation stage. It's debatable, with regards to viewport transformation, whether that viewport transformation has to happen here or whether it can still happen here or after the rasterization stage. Most modern graphic systems, to my knowledge, do viewport transformation first. and then do rasterization. There's trade-offs, I guess, both ways in terms of the data types you're dealing with, and what the range of your input vertices is going to be in positional space. So primitive assembly is the next step, and that's where we're going to be leaving things off for today. So going back to our trapezoid, and I think your question's right on point with regards to this. Um, GL triangle strips, for example, have very specific rules about how they get assembled. So I said vertex assembly. That is the right term. That's that's like data fetch. Maybe data collation is what your vertex assembly is, right? It's all the attribute data associated with a single vertex. Read it from memory and give me the next one. That's vertex assembly. It's not so hard for us because it's just a block of data. So give me the next chunk of data in memory, and I'm calling that my next vertex. Primitive assembly can also be simple, right? For GL points, and you may have seen this in the hardware module that we call our primitive assembler, there's nothing to assemble. The vertex is the primitive, so you're done. You're just passing it on. For triangles, it's not so hard either. Give me the next three, and that's my triangle. For these other couple of these other data types, you have to be a little bit careful with it. So for a triangle strip, this is just the definition of triangle strip. People ask me that, and we labeled them in that picture, which is from the OpenGL spec. A, B, C, D, E. Maybe starting with 0 makes a little bit more sense, but it's the same concept. For a triangle strip, the first three vertices specify the first triangle. And then if you want to think of it as like a little stack, or just think of keeping track of the most recent two vertices, every additional vertice after the first three then also specifies a new triangle. So when you have to get to your question, when you have four of these, it's going to look very trapezoidal potentially, but it doesn't have to be either, right? That fourth vertex here could have been in all sorts of locations, and I have to think about it a little bit. If I had specified this fourth vertex down here, it would have been an interesting output, right? The shape as a whole would have been non-convex, but it would have been broken down into two convex triangles no matter what. So the actual color of the stuff happening here, it really would depend on the rasterizer what it would turn out to be. But that's why these triangle strips work. The triangle strip itself, it can be a pretty arbitrary shape at the end of the day, but by definition, by spec, it gets broken down into triangles. So we don't have a trapezoidal rasterizer. We have no way of guaranteeing that given four vertices, it's actually a trapezoid or a rectangle or anything of that. We have a triangle strip where its first three is a triangle, then every additional one takes the previous two and forms a triangle out of it. If we have vertex 5, if we put it over here, maybe easier to visualize, 2, 3, and 4 would be that third triangle we would generate here. So the rasterizer, as part of that setup step for it, is doing this primitive assembly. And for us, and I think this is where we want to stay in terms of what we implement, at least in hardware, for us, primitive is then synonymous with triangle, at least after that step. Triangle are points for us. So it's either pass-through points because the vertex is the primitive and we're done. Don't do anything. Don't even engage this hardware block generally, right? Or we break it down into triangles, and then we've assembled our primitive. We have this OpenGL spec of a triangle strip. For us, we're outputting triangles, and that's what becomes our primitive. So that's okay. And we already talked about it. What about the different approaches for different kind of arbitrary primitive types? Things like, can you rasterize something like this properly? There are algorithms to do them. They're fairly complicated, and so whether or not we want to consider all of our primitives as triangles, I think the right way to state it would be, it's not really correct to say that everything we specify is a triangle, but our life is a lot simpler if we assume that all of our primitives that we're actually rasterizing is going to be triangles. And so even with programmable tessellators and geometry shaders, to my knowledge, we are still just decomposing things down to triangles in modern GPUs. The algorithms are well understood for how to do that rasterization. We don't have to worry about all sorts of weird edge cases for them. And so for our primitive assembly module that we're building, our job isn't that hard. So I'd like us to take time, and I'm going to try to split you up into teams for the last 5 minutes that we have here, and consider this exercise. This is actually a harder exercise than what you're having to do for the lab, but it's easier because you're just doing it on paper, so it's a lot easier than what you're doing for the version in the lab. So I'd like you to consider either software algorithm, state machine, flowchart, however you want to do it, that takes input vertices as well as, and people already caught this, which is great from the MP2 spec, um, some way of information that tells us that we're done, because we do need to know that for these primitive types. We have to have a way of saying we're done sending data associated with a triangle strip or a line strip or a line loop or a triangle fan. We have to have a way of knowing that this primitive, OpenGL primitive, is done. We're now drawing the next OpenGL primitive. So consider that as an input to your state machine called we're done or end with this primitive. The GLN was the kind of old school way of specifying that, as well as then as an input, which is the primitive type, which could just be any of those enumerated types on the slide here. And your output should be actual primitives. So I'm gonna break you into groups of 3 here, and say hello, to your friends. My understanding is you won't see this slide, and you won't see my screen once you break into groups. So you can open that up in Canvas. This lecture for information that we have here, and open that up in Canvas and take a look at that with your team. And let's just take the last 5 minutes we have today and see what we can come up with for doing this, and we can report back on next week on Tuesday. So you haven't been used to having to speak up all that much. This is our first attempt in doing so. We'll see how it goes. So we're going to create 8 rooms, and no, you cannot choose which room you're in. You technically have to agree to join the room, but please agree. Yeah, well, that's a good line, Ryan. And unfortunately, this also lets me know who's not really paying attention today, so that's unfortunate. But yeah, that's fine. I'm not going to call you out on that. Um, okay, thanks for joining. I like it. That's a good idea. And I feel. Oh, it looks like we lost everybody. Did they just leave, or did we get put into a room at the same time here? Well, I certainly hope people didn't head out. Okay, they're starting to make their way back. I was worried. It looked like there was nobody here briefly, and I thought it was done. Well, in the interest of time, you can check out here, so we can be done for today. So let me know. Post in Discord if you have any questions about this exercise we just did. Um, Obviously, that 5 minutes isn't enough time to really confirm it, but your state machine should look roughly the same when you do it in hardware. There's really no more to it than that, which is wait for new vertex based on which primitive type you're currently expecting, which driver has to generate that information for us. But based on the primitive type you're currently expecting, um, spit out assembled primitives. And for us, it's okay because, well, if we had to do points, lines, or triangles, we would really need to have three separate pieces of hardware to support that. Points don't require much. Lines would require presumably a different line rasterizer, or we could treat it as a very skinny triangle. And then triangles would be then the third rasterizer. But from our perspective, if we treat everything as a triangle, we should be able to then have a very simple output for this component. So I know no one would have gotten this done just in the 5 minutes you had working with a random person in the class or two other people in the class. But your code that you you implement that for MP2 should look pretty simple, similar to the state machine you would have come up with right now. There's no weird edge cases for this. So given the type of primitive, if we assume the OpenGL code is well formed, I guess you can do all sorts of weird things in your OpenGL. Assuming certain restrictions on our OpenGL input and the vertices that are being passed, you should be able to generate your output triangles accordingly. Let's leave things here for today. We'll really jump into the rasterization topic. I think the timeliness is still pretty good. We'll get to the meat of the topic before you have to implement it all in the lab, unless you get ahead of the rest of the class, which would also be great. So leave things here for today. Look forward to seeing progress people make over this weekend.